So last day, we talked about the importance of polyunsaturated oils and unsaturated oils with regard to melting temperature. And when we talk about the structuring of fats, it's dependent on the chain length of those fatty acids, the degree of saturation of those fatty acids, but also the distribution of those fatty acids on the glycerol backbone. So we talked about the fact that most fatty acids follow a restricted random process, right? Where certain fatty acids are preferentially located on specific points within that fatty acid. And the example we gave last time was cocoa butter, where cocoa butter preferentially puts the unsaturated oleic acid at the SN2 position. Now, does anyone remember the process which randomizes where those fatty acids are on the glycerol backbone? We mentioned it briefly. No? Esterification. So esterification is that randomization of the fatty acids on the glycerol backbone. This is important when we talk about margarine production today, which we'll talk about a little bit later. First, we're going to talk about hydrogenation. So hydrogenation was originally developed to try to increase the degree of saturation of plant-based vegetable oils. And the reason this was done was because animal fats, one, being very expensive, but also the fact that they were fully saturated. And in the 70s and 80s, there was a real push against saturated fats being detrimental. And we'll talk about that in a little bit. So the idea, though, was that we were going to hydrogenate, add hydrogen to those double bonds to create some of that unsaturated oil to be saturated. And this way we could turn a liquid oil into a solid, what we term plastic fat. So we could take very, very inexpensive things like soybean oil or canola oil or corn oil and turn it into functional fats that behave similar to butter and lard. The benefit to doing hydrogenation is that it increases the stability of that liquid oil. Right? So remember when we talked about oxidation? The rate of oxidation is dependent on how easy it is to extract the hydrogen. And where are those labile hydrogens when we talk about unsaturated oils? They are one carbon removed from that double bond. And do you remember why they're more labile or more easy to remove? What can happen once we create that free radical? We get isomerization, right? We can get the shifting of that double bond. So by eliminating double bonds, we decrease the oxidative susceptibility of that oil, and it makes it more heat stable. So it makes it more solid-like, and it makes it more stable to frying applications. Now, the downfall to hydrogenation is if you do not fully hydrogenate it, you get the formation of cis and trans isomers. So you get the introduction of transaladic acid. And we talked about other trans fats that are naturally present in our diet coming from the biohydrogenation occurring in the rumen, right, of milk. So we get two fatty acids that are present in milk that are in the trans conformation, which are your transvicinic acid as well as your conjugated linolenic acid, or CLA. Now, when we talk about trans fatty acids that are derived from milk products, there's a lot of discrepancies on whether or not they are beneficial or detrimental. So there's a lot of reports that CLA have beneficial health outcomes. And there's a lot of evidence that suggests that transvicinic acid doesn't have the same biological outcome as industrially produced trans fats. Trans fats that are produced by the hydrogenation process. So when we talk about, again, the melting point of fats, they're determined by the way those fats or lipids interact with one another. Remember we packed those chairs together and we talked about the unit cell and the subcell? Well, that unit cell is dependent on how linear that chain of fatty acids is, or that aliphatic chain is. So the more linear or the more straight it is, the higher the lower the melting, the higher the melting temperature, yes. So if we have a saturated fat, we can envision that it's relatively easy to pack those fatty acids together. if we introduce a cis double bond, it impedes that crystal structure. It makes it more difficult to pack into a crystal. If we convert that cis fatty acid into a trans, we can see that it packs in a very, very similar fashion to saturated fatty acids. So the melting behavior of a trans unsaturated fatty acid behaves remarkably similar to that of the saturated counterpart. So for a long time, it was believed that if we keep that unsaturation, but we've converted it to a trans unsaturated, we could get the elastic properties that's desirable in a fat, so we can get that crystal structure while maintaining the nutritional benefit of the unsaturated oil. We now know that this is not true. Industrially produced trans fats have no beneficial biological outcome. So trans fats that are produced via hydrogenation or industrially produced trans fats are not biologically good for us. So hydrogenation is and will continue to be a very, very important process in the food industry. So hydrogenation requires a catalyst. Usually it's a heavy metal, something like platinum or nickel. We need hydrogen gas, and we need some sort of temperature. So we need gas, we need pressure that comes from the gas, and we need a catalyst. And the reaction that takes place typically occurs at elevated temperatures, typically somewhere between 250 and 300 degrees Celsius. Now, when we undergo hydrogenation, the process is dependent on what the desired outcome is. So when we talk about the production of trans fats via hydrogenation, we're really referring to partially hydrogenated fats. Partially hydrogenated fats always lead to the formation of trans fats. Fully hydrogenated fats do not lead to the production of trans fats. And this is really, really important messaging to get across to consumers today, because there's the impression that all hydrogenated fats contain trans fats. This is not true. Again, partially hydrogenated oils and fats will have trans. However, fully hydrogenated fats will only contain saturated fats. Now, why is this beneficial? We can take a low-value commodity, something like corn oil, soybean oil, sunflower oil. We can fully hydrogenate it. If we fully hydrogenate it, the melting point goes up, we have a hard stock fat, and then we can blend it with other oils. So we could take, let's say, a fully hydrogenated soybean oil, mix it with an non-hydrogenated oil, blend it to a ratio of whatever the specific ratio is, and we can get an elastic fat that has properties that we want. So depending on how hard we want that fat, we can change the ratio of the fully hydrogenated hard stock to the unhydrogenated liquid stock. And this is the basis now for all margarine-based products. So if we look, see, all right. Turn on the light. That doesn't show up very well. Turn off the light? No. So, irrespective of the product, if it's a butter or a margarine, both of them have about 70 calories. The difference is that margarine contains no animal fat. So in this product, in Basel, if we look at the ingredient label, the first two ingredients are canola oil and sunflower oil. Both of these, well, canola is primarily a monounsaturated, sunflower is mainly a polyunsaturated, so it's a liquid oil, contains water, and then it contains modified palm oil. Now, modified palm oil is fractionated. Now, what does that mean? So if we take palm oil and we cool it down to a certain temperature, we can get the hard stock or the saturated fats to crystallize out of solution. So fractionation is really just the partial crystallization of fats, and then you separate out the liquid and the solid fractions. And palm oil is fractionated numerous times. So there's numerous fractions we get from palm oil. So palm oil, in this case, would be the hard stock, meaning the fully saturated fat. It gives the product its elasticity. It's going to be a hard lecture. I'm dying of another cold. I swear, my youngest brings home something different every day. So if we compare, these have both been sitting out for a while, the structure of butter and margarine, I'll use the lid here. So you can see, I'm trying to put about the same amount of force. Butter resists that flow very well, whereas margarine is much softer. The reason for that is they're trying to maximize the amount of unsaturated oil you get in margarine. So the argument being that unsaturated oil is better for you than saturated, which we'll talk about at the end of class today. So when we talk about hydrogenation, it's that ability to convert a liquid oil into a solid fat. And again, when we talk about solid fats in the food industry, we really only have animal-derived fats, so lard and butter, and the other one that's solid at room temperature is cocoa butter and shea butter. If we want to utilize vegetable oils, we have to convert them to a chemical structure that's conducive of forming a crystal network. Again, this is done through the process of hydrogenation. Now, Bruce Holub and David Jenkins were instrumental in understanding the cardiovascular risk associated with consuming elevated amounts of trans fats. And Bruce Holub, again, is a professor emeritus here at the University of Guelph. Now, does anyone know why trans fats are detrimental for health? What is it that they do that increases the risk for coronary vascular disease? Yes? No, they're not more reactive. Yes? Sure. So the question I'm asking is, what is the biological change that happens when we consume a diet high in trans fats? What happens to our cholesterol? Which cholesterol goes up? The LDL or the VLDL, right? The low density lipoprotein or the very low density lipoprotein. Trans fats increase the amount of trans fats increase the amount of LDL and VDL, and they simultaneously decrease the amount of HDL. So remember, when we talk about coronary vascular disease and cholesterol, it's the ratio of those two that determine your risk factor for coronary vascular disease. So you want a low ratio, meaning you want a high HDL and a low LDL. Trans fats, again, increase your LDL and decrease your HDL, so they decrease that ratio. The decrease in that ratio has biological outcomes that put you at risk for coronary vascular disease. So much so that Canada banned trans fats, which has just gone into effect now during this course. I forget the exact date, but it was only a few months ago. So when we talk about hydrogenation, again, hydrogenation removes double bonds. So if we start with 18:3, or linolenic acid, we add 2 hydrogens, we convert linolenic acid to linoleic acid, we add 2 more hydrogens, we convert it to oleic acid, we add 2 more hydrogens, and we convert it to stearic acid. As we do that, we increase the melting temperature and make that fat go from a liquid to a solid. Now, how can we increase the selectivity of that fat? Meaning, how can we ensure that the reaction progresses? So we're going to come back to this a couple times, but we have to know how the chemistry of hydrogenation works to understand how to tailor the process. So what we have is our metal catalyst. So we'll draw that like this. So this is just our metal. And what's nice about this is we can continually recover that catalyst and we can reuse it and reuse it. So we have our catalyst, we add hydrogen gas, and then we add our unsaturated oil. Now, because of that unsaturation, that can form a covalent bond with the catalyst. So that unsaturated oil, that pi bond, forms a covalent bond with that catalyst, breaking that double bond. And now that means we have a radical. If hydrogen is in close proximity, hydrogen will react with that. This causes this bond to break, and a second hydrogen comes in here. Now, in a process where you have excess hydrogen, so you have a lot of hydrogen, this process is going to go to completion. The higher the temperature, the less catalyst, the more hydrogen you add, the more likely you are to go to completion. Meaning that when this bond breaks, this is going to form a saturated bond. Make sense? Okay. Now let's say we limit the amount of hydrogen. So it forms this unstable complex with the nickel, breaking that double bond. When that happens, we now have free rotation, right? So if no hydrogen's present, this bond breaks, reforming that double bond. Now when this double bond reforms, it can either go back to the cis configuration or it can form the trans conformation. It preferentially forms trans because it is energetically more favorable than cis, but not by much. So it'll form about 60% of the time it'll go back into the trans configuration, 40% of the time it'll go back into the cis configuration. Make sense? So what we do now typically is we don't undergo partial hydrogenation. So partial hydrogenation again relies on some of these double bonds remaining intact. If the double bonds are remaining intact and we're doing partial hydrogenation, we're going to limit the amount of hydrogen gas in that system, so we're not going to put in excess hydrogen. This means that we get that temporary bond between the catalyst and the unsaturated fatty acid. When that temporary bond forms, we get free rotation around that pi bond, which allows it to reform in either the cis or trans configuration once that temporary bond with the catalyst breaks. So again, fully hydrogenated processes or complete hydrogenation will convert all of that all of the unsaturated fat into saturated. Partial hydrogenation leaves some of that unsaturated oil in its unsaturated state. The difference now being that instead of having just a pure isomer of cis, we're going to have a mixture of cis and trans. And it's the trans fatty acids that are very, very detrimental. So here's the process. So when we start hydrogenating any vegetable oil, we typically have a mixture of the four different 18 carbon fatty acids. The four 18 carbon fatty acids is saturated stearic, so 18:0, oleic, which is 18:1, linoleic, which is 18:2, and linolenic, which is 18:3. As hydrogenation progresses, the amount of linolenic acid decreases. As the amount of linolenic acid decreases, the amount of linoleic acid decreases as well. Now, oleic acid, which is 18:1, originally increases. And what would drive the increase of oleic acid? Why would we be forming oleic acid during hydrogenation? Because we're preferentially adding it to the 18:2, which is then going to the 18:3, which goes to the 18:2. When we add hydrogen to the 18:2, it becomes oleic acid. So linoleic is converted to linoleic, linoleic is converted to oleic, and then oleic is converted to stearic. So during hydrogenation, we can monitor the amount of stearic acid. This is going to be our plastic or our solid-like fraction. The more stearic acid we produce, the harder that fat will become. Yeah?
Explain again how oleic acid eats so much more than stearic.
So oleic is going up because linolenic, so 18:3, when it's first hydrogenated, 2 hydrogen goes on. That then becomes linoleic. When we add 2 hydrogen to that, we begin to form oleic. So what that means is, as we're depleting linoleic, it is converting into oleic.
But aren't you also not depleting oleic to make it stearic?
Yeah. So the rate in which we're adding 18 to 18.3 and 18.2 is greater than the rate we add to 18.1 because they're more unstable. So even though we're producing oleic here, we're still consuming some of it. So it's not like there's no oleic being converted to stearic. You can see that stearic's automatically starting to rise. So right away, some of that oleic is being converted into stearic. So we tailor the process in partially hydrogenated fats to have that exact ratio of stearic acid we want. So we could say we want an intermediate hard fat to be used as a convectionary fat, so we're going to partially hydrogenate that oil so it's 40% saturated. That process, that partial hydrogenation process, we no longer do. The reason again for that is partial hydrogenation leads to the formation of trans fats. So what we do now, instead, we hydrogenate that fat fully, so 100% of that fat is hydrogenated, and then we mix that with unsaturated vegetable oil to get that ratio we want. That's termed blending. So when we talk about, I can't believe it's not butter, Basil, these fats all rely on blending of oils. We take a fully hydrogenated hard stock or a palm fractionated oil, so both of those really high in saturated, and then we mix that with unsaturated oil. Now, if we look at our label, we have in butter 5 grams of saturated compared to 1 gram of saturated. So that's 5 grams per 10 grams in butter. So half of the weight of this, and more than 60% of the fat in butter is saturated. In this product, 1 gram out of 10, so 10% of the product is saturated, and 1/8 of the fat is saturated. So this product is much, much softer than butter. But not only that, if we just mixed 1/8, let's say fully hydrogenated canola oil with sunflower oil, we would get a phase separation, meaning our crystals would sink to the bottom and we would have a liquid oil. So what do we add? We have to add all kinds of things to this product that modify the viscosity of that water phase. So in this product, we have buttermilk powder. So we have proteins. We have soy lecithin. So remember what lecithin's good for? Anyone remember? It's a good emulsifier. Is there anything else in this one? Nope. So this one has buttermilk powder and lecithin. I can't believe it's not butter. Another one that's similar. So if we look here, in a 10-gram serving, we have 1.5 grams of saturated, so a little bit higher than the base L, and 1.5 grams of saturated per 6 grams of total fat. Now this one, we can see that we add, so it's soybean oil, canola oil, or vegetable oil, water, modified palm kernel oil, so those are our fractionated hard stock fats. We add buttermilk powder, which is again your protein. But now we add vegetable monoglycerides. Monoglycerides are a good surfactant. We add soy lecithin, again, a good surfactant. And I think that's it in this one. Yeah. Now, when you get into the low-fat products, you have to begin to structure the water phase with polysaccharides. So you'll see different gums being added to the low-fat margarines. So again, when we talk about this process of hydrogenation, that partial hydrogenation, where that double bond interacts with the metal catalyst, breaking that double bond, if it's partially hydrogenated, we don't fully saturate that unsaturated oil. As a consequence, when that bond breaks, we can have cis-trans isomerization. The degree of cis-trans isomerization is dependent on the temperature, on the pressure or the amount of hydrogen gas we have, as well as the rate which we're mixing. Basically, it all has to do with how available hydrogen is at the surface of this catalyst. The more hydrogen that's available at the surface of the catalyst, the less likely this is to form a complex and then break without forming that hydrogen or that without forming that saturated fat. So what does that mean? We have two scenarios. If we're completely devoid of hydrogen, a reaction occurs, so our double bond reacts with the catalyst. If no hydrogen present, this is going to break and reform a saturated. If we completely saturate the surface of that catalyst with hydrogen, when this bond breaks, there's going to be ample hydrogen to break that double bond, converting it to a saturated fat. So it is dependent, the selectivity of the reaction is dependent on the amount of hydrogen that's present at the catalyst interface. So this is dependent on the concentration of hydrogen, the temperature of the system, and the degree of shear. And we can tailor this process to try to reduce the amount of trans fats, but again, in partial hydrogenation, you cannot eliminate the formation of trans fats. To ensure that we don't get any trans fats, we have to fully hydrogenate that system. Make sense? Yeah.
So I'm just a little bit confused. So the point of doing the full saturation mix with the unsaturated oils is to reduce the amount or the possibility of creating trans fats.
Right.
So why wouldn't you just take a product and completely saturate it and have a completely saturated product?
Because it's so unfunctional. It would be, I'm trying to, have you ever, what's a good example? There's some lipsticks that are high-fat products and they're like a wax. That would be the consistency of that product. So from a food application standpoint, it doesn't have a lot of functionality. So what they typically do now is they make an ingredient that's fully hydrogenated, that's like a wax. They blend it with some unsaturated oil and they make a mixture of it. Now, the downfall to doing that, or I shouldn't say the downfall, but what happens with that is you get two very, very diverse clusters of triglycerides. So you'll get a subspecies of triglycerides that are unsaturated and a subspecies that's fully saturated. This results in a very, very sharp melting profile, right? Because it's either fully hydrogenated or not hydrogenated at all. So these melt all at really similar temperatures. These are liquid. So what we get then, and this isn't desirable, is a melting profile. So this is solids. This is temp. So what we see are melting profiles that look like that. What typically in butters and margarines, what we want is a much more gradual profile. So what we do now is we blend these two fats and then we intersterify them. So then what we do, so intersterification randomizes where those fatty acids are. So it can actually switch an unsaturated oil off of this triglyceride, which is unsaturated, onto this fully hydrogenated one, and one of these saturated ones go onto here, and that broadens that melting temperature. So that's what we term intersterification. So all of these new novel margarines where we try to get really functional properties, we fully hydrogenate one of the vegetable oils, we blend them, we intersterify them, and then we get really functional fats based on that.
Okay, and the reason for that is because most of the plant-based saturated fats are the same as the animal-based saturated fats.
So, what do you mean?
So there's different kinds of saturated fats, right? And the ones that are in animal-based products like butter
Yes?
have the better properties.
Right. So, yes. So of the hard stock plant-derived saturates, they are mainly musteric and palmitic acid, so C14, C16. Animal-based are typically C16, mainly C18, and a little bit of C20. So the chain length differs between saturated fats in plants and animals. Now there is overlap between the two. Really the reason we do it is cost. You can produce a fully hydrogenated, blended, intersterified vegetable oil-based product cheaper than you can create an animal-based fat, or like let's say a cocoa butter or a shea butter. So it's cheaper to make a cocoa butter equivalent out of this process than actual cocoa butter.
And in terms of health, are they similar?
We'll talk about that in a couple minutes. It's coming.
Would you use partial hydrogenation for manufacturing, let's say, cosmetic products that you're not necessarily consuming?
I don't know. I don't know how relevant it is in the cosmetic industry, to be honest. You could. I would find it hard to imagine there'd be any risk of applying trans fats dermally. Yeah, so I would think it would be fine, but I don't know. Okay. This section is going to be tricky for me. So I struggle with whether or not, what messaging I want to give centering around trans and saturated and unsaturated oils. So remember, when we talk about lipid digestion, so we've already talked about this, we have that release of CCK, that CCK, cholecystokinin, causes the gallbladder to contract, releasing the bile. That bile is made up in the liver from cholesterol, and that bile is secreted and conjugated with either glycine and tartarine. This acts as a surfactant. Remember, that oil phase is in a non-similar phase as our enzyme. The enzyme is in the aqueous phase. It needs to react with the apolar phase. So bile acts as an emulsifier to allow lipase to interact with that interface. Now, when that does that, the enzyme comes in and it cleaves off the two fatty acids at position 1 and 3, leaves the position 2 fatty acid alone, so we get a 2-monoglyceride. That 2-monoglyceride and the 2 fatty acids are absorbed and then are reassimilated in the epithelial cell. And then this chylomicron is that assembled triglyceride plus phospholipids plus cholesterol and then this beta lipoprotein. When we talked about lipid digestion, we really brushed over the fact that this beta lipoprotein plays a very, very important role, and we'll talk about it. So, the lipoprotein, again, remember, oils are not soluble in water, right? So when we want to circulate a lot of oil through our system or through water, we have to pack it into micellar structures. And these micellar structures minimize that interfacial free energy between the water phase and the oil phase. So what we get, I'll jump back to this, no I won't, I'll do it from here. So what we get are these little particles that are rich in triglycerides and cholesterol within the core of that micelle, and then all of these amphiphilic molecules surround the outside of that molecule. So phospholipids, bile, those are surface active molecules. In circulation, the two big ones are phospholipids and your lipoproteins that reside on that interface. The phospholipids specifically are the amphiphilic molecule that reduce the interfacial tension and allow it to exist as a droplet. If we didn't have that lipoprotein at the interface, we would get coalescence of that fat within our arteries, which would be very detrimental. So when our body absorbs fat, remember that fat is reassimilated into the triglyceride, it's packaged with any cholesterol and lipoproteins. This then goes into the lymphatic system through and picked up by the hepatic portal, it goes through the lymphatic system, ends up at the liver, where it is either stored or metabolized. Now, when fat comes from the intestinal tract, it has lipoprotein B on the surface. Now, lipoprotein B is just a fat covalently bound to a protein. That allows that protein to act almost as an enzyme or a metabolic signaling pathway. So if we have lipoprotein B on the surface, it's going to trigger certain tissues to pick up that fat. And depending on where that droplet or where this lipoprotein is coming from, if it's coming from our intestinal tract and going to the liver, or if it's going from the liver back into circulation, or if it's coming from circulation back to the liver, the lipoproteins on the surface of these droplets change. So their metabolic fate changes. So what we typically think is that VLDL, very low density lipoprotein, comes from the intestinal system carrying the fat to the liver. The liver is deposited the fat is deposited in the liver, and then it's repackaged. And it can be repackaged so then it goes into circulation and goes and gets stored into adipocytes, right? Now, when we have too much free fat, we have to have a mechanism to pick that fat back out of our body or out of circulation, bring it back to the liver where it can be metabolized. So this pathway, or where those particles are coming from, will actually have different lipoproteins on the surface. Now, the chylomicron is what takes the oil from the intestines to the liver. It is comprised mainly of oil and has very, very little cholesterol, very little phospholipid, and also, but the most important, it has the least amount of protein. So this goes to the liver from the intestines. Chylomicrons spike after you consume a meal with a lot of fat in it. Now, the VLDL transports fat from the liver to various sites where it is needed. Again, VLDL contains a lot of fat, but it contains a lot more protein. Chylomicrons, VLDL, LDL are considered the detrimental cholesterols because they are so rich in fat. Now, what's interesting about these is they are dangerous because they can undergo oxidation. What fats are undergoing oxidation? Your unsaturated oils. So this is where fat trafficking, cholesterol trafficking really gets confusing. Is because even though unsaturated fats are better for us, they are the ones implemented in arterial vascular narrowing. So when arteries narrow, we'll talk about in a second, is due to the oxidation of this fat. Now, HDL is very unique in that it has a very, very high protein concentration and a very, very small fat. So HDL goes through circulation, picks up any triglycerides that are excess, brings them back to the liver where they can either be stored or metabolized. So we want high HDL, low LDL. So far, does that make sense? Yes?
Is kind of micron eventually going to convert into HDL as it moves through?
Not really. So it's a great question, and it's not really an easy question to answer. So all four of these are in circulation all the time, right? So you eat a meal, you have your chylomicrons spike up. Now, when those chylomicrons are in circulation and HDL is in circulation, they have different lipopolysaccharides on the surface. If those two droplets come into contact, they can actually begin to exchange materials. If HDL begins to transfer its alipoproteins to a chylomicron, that then becomes VLDL. Now, chylomicron can convert to VLDL, VLDL can convert to LDL. HDL is synthesized from the repackaged materials of these constituents in the liver, but it's a completely new assembly. Does that make sense? Okay.
Also, depending on the size, does the VLDL have more fat than a chylomicron? If it's just based on percentages?
It would be irrelevant. It could, but the overall trends follow this pattern. So there's variability within particles, and as particle size changes, that composition would change, and there would be a distribution for chylomicrons, VLDL, LDL, and there would be overlap between them. Okay. So when we talk about, again, yes?
I just had a question. Why is oil and CBD like proteins here the most detrimental?
Because the chylomicron is only associated in the fed state, not the fasted state. So we don't typically see as much chylomicron as we do VLDL when you're in the fasted state.
Did you say it was unsaturated or saturated oxidation?
Only unsaturated oils undergo oxidation. Saturated, we would have to actually boil our human body to get those to oxidize, so it would never happen. Okay, so depending on where this fat is being trafficked from and to, that the protein that's esterified to the fat changes. So ApoB is associated with detrimental effects associated with coronary vascular disease. So if you have a lot of VLDL or LDL, your ApoB will be elevated. If you have a lot of HDL compared to LDL, your ApoA will be elevated. So we always look at the ratio of your ApoA to your ApoB to determine your coronary vascular risk. The reason this is important is when you get injury on an artery wall, you tend to get the accumulation of these lipoproteins. Now, when they begin to accumulate, they begin to oxidize and they turn into what are called foam cells. And these foam cells are the basis of arteriosclerotic plaques. So that arterial hardening is associated with VLDL and LDL, high levels of ApoB, which is being formed into these foam cells, which then narrow the artery. So we want low levels of ApoB. The reason for this is plaque is insoluble. It's mainly made up of fat. So to treat plaques, we either need a really high amount of HDL to pick up that fat that's been deposited. This is not a very effective way to treat it. We need enzymes that actually break down that plaque. So the question I always get in this course is, what should I eat? Butter or margarine? And this whole debate started in the 1970s. And what they did was they compared Eskimos living in Greenland versus Eskimos who had migrated and live in Denmark. And what they found was, so remember, the beta lipoproteins are detrimental. So these first two columns are associated with our LDL and our VLDL. Our alpha lipoprotein is our HDL. And what they found was the Danes, so the Eskimos living in Denmark, had higher levels of our pre-beta and our beta. So we can see elevated levels, elevated levels, elevated levels for the men, and we could see elevated levels for the women, and they were statistically different. So the argument cannot be made that this is an evolutionary trait, that they have more beta-producing lipoprotein, because again, they're from the same lineage. The conversion or the moving to Denmark was done within that generation. So it's a really interesting study that found observationally that diet influences the ratio of our beta versus alpha lipoproteins. So again, bad cholesterol, good cholesterol. Now, what they didn't find was the effect of HDL was not significant in women, but was significant in men. So that was interesting. Now, the downfall to this study was that the population of West Coast Eskimos that they selected were people who typically did the hunter-gathering diet. They had very physical lifestyles. Exercise is known to contribute to HDL. So it's not surprising that HDL was more impacted in the male population of the West Coast Eskimos than the female population, because in the 1970s, the hunterers were most generally male. Now here's the observation that kind of made it really famous, was what we found was a significant increase in Danish women for total lipids in the circulation, for total cholesterol in circulation, triglycerides tripled, phospholipids were not significantly different, our 2 beta, so again these are LDL, VLDL, drastically increased, more than doubled, and our HDL didn't change. So this showed that consuming diets that the Denmarks were consuming compared to the Greenland Inuit led to higher cholesterol levels, higher detrimental cholesterol. Why? What was the major difference between the two diets? The Greenland Eskimos relied mainly on a diet of seal, whale, and cold water fish, all high in polyunsaturated oils. The Denmark Eskimos relied more on the Western diet, which was far greater in saturated fats. Now, this study does not show cause and effect. Epidemiological observations can never provide cause and effect. So although this variable was seen, there is no conclusive evidence from this study that says that it was the saturated versus unsaturated oil. Make sense? Okay. Next, what they did, or more recently, is they took liver cells. Now, when they exposed these liver cells to either saturated, unsaturated, or trans fatty acids, they looked at the regulation of this transporter, or what, excuse me. Ugh. So, sorry. PGC1 beta plays a very, very important role in trafficking of lipids. So when we have a high amount of lipids in the body, we typically store them in the liver. So if you become clinically obese, one of the typical side effects is you get a fatty liver. Now, if you upregulate PGC-B1, it pushes the fat out of your liver and into systemic circulation. When fat leaves the liver, it is packaged into your VLDL. So anything that upregulates PGCB1 will increase lipid trafficking or your VLDL. Yeah?
I'm just confused about what you said. The AUSD for the polyunsaturated fats from eating the animals as opposed to saturated?
Right.
I'm confused.
Okay, so we have to look at kind of the food tree for whale, seal. So whale, seal, cold water fish all consume microalgae. Those are very, very rich in polyunsaturated fats. So their meat content and their fat composition is very high in polyunsaturated oils, just like cold water salmon, let's say, compared to a Western diet, which is much higher in saturated. Other questions? Okay, so again, this PCGB1, if it's upregulated or if it is increased in expression, it's going to push the fat that is stored in your liver into VLDL into circulation. So upregulation of this PGCB1 is going to increase our VLDL and our LDL. So what they did is they took hepatic cells and they measured the expression of this. And what they found was monounsaturated fats only slightly increased PGCB1. So that means that an unsaturated fat will very minorly increase the VLDL. When they gave saturated fats, it increased the amount of VLDL production. But what they found, which was remarkable, when they put trans fats, it tripled the PCGB1 expression, which means your VLDL goes way up. So we have this observation that people that eat cold water, marine-based diets are less likely to have high levels of bad cholesterol. The other observation they made of the Eskimo, they had very, very low incidence of coronary vascular disease. Instead, they were typically dying of strokes and diseases related to strokes. So increasing trans fats increases lipid trafficking out of the liver, increasing VLDL. Saturated and monounsaturated have a far less increase on that trafficking, meaning it doesn't increase the VLDL as much. Now, has anyone ever heard of a Cochrane review? So, for those who don't know what a Cochrane review is, if there's anything in nutrition that you're doing a review paper on in university, the first place you should go is to the Cochrane reviews. They are non-biased, and I'll put that in quotation marks, authors who write assimilation papers that review all of the current literature. So they take into account all the literature and then formulate an opinion based on what's published in science. So this is kind of the trending, most current opinion on whether or not saturated fats are good or bad for us. Do you have a question? Oh, no? So, I took the conclusion, so this is the Cochrane review for should we reduce the amount of saturated fat intake for coronary vascular disease. And here are the statements. Long-term trials suggest reducing dietary saturated fat reduce the risk of cardiovascular events by 17%, but not the effects on mortality. So you weren't more likely to die of a heart attack if you had a reduced saturated fat. Some evidence that reducing saturated fats reduce the risk of myocardial infarction, so heart attacks, but evidence for non-fatal myocardial infarctions were less clear. Subgrouping suggests that reduction of coronary vascular events was seen in studies that primarily replaced saturated fat calories with polyunsaturated fats, and no effects were seen replacing saturated fats with carbohydrates or with protein. But effects were unclear. So really, the Cochrane review right now for saturated fats is, it's not really clear on what role saturated fats play in the diet. So, what do you say then? So the first thing we have to consider as a nutritionist and as a food scientist is, if we're going to replace the saturated fat in a food product, how do we replace that functionality, right? Saturated fats are the basis of the solid fats we consume. Cocoa butter, lard, butter, margarine, cookies, cakes. They get their desirable sensory properties based on the saturated fats. If we take that saturated fat out, we have to replace it with something, right? Not only from a composition standpoint, we've got to equal 100%, but also from a functionality perspective. We have to put something back in to make that product have a desirable sensory attribute to it. So what can we replace those saturated fats with? We can either replace it with proteins or carbohydrates, so we can reduce the total amount of fat intake, or we can substitute monounsaturated or polyunsaturated fats. The downfall, or the technical challenge with replacing them with unsaturated oils, is that solid product becomes a liquid product, right? So you're not going to buy a chocolate bar that's melted, or you're not going to buy margarine that has the viscosity of liquid oil. So you need that functionality. So there's certain limitations of the food product that's going to dictate what we can add back into that product. So what this study did was it took 5% of the energy, 5% of the calories of saturated fats were removed from the diet and replaced with either unsaturated, just a general term, monounsaturated, polyunsaturated, trans, omega-3s, or omega-6s. So by changing our saturated fat to just a mixture of unsaturated oil, in this one here, we see total mortality. Shifting this way is beneficial. Shifting this way is detrimental. Man, this slide doesn't show up very well on this. It'll be in the slide deck once we post it. But here, so if we replace it with 5% unsaturated, we see a minor increase or decrease in the relative risk of death. If we replace it with monounsaturated, we see less of an effect. Polyunsaturated, we see a more beneficial effect. Again, the more we go this way, the longer your longevity or the lower your mortality risk. When you go this way, the higher your risk for mortality. Trans fats shift drastically to an increased risk of mortality. And then your omega-3s and your omega-6s have a beneficial effect. Now, that's overall mortality. If we look here, this is coronary vascular disease. Again, this shouldn't be surprising. The messaging on this is pretty clear. Replacing saturated fats with unsaturated oil, beneficial. Replacing it with monounsaturated is barely beneficial. You know, depending on the standard error, it may have no effect. So if someone were to say, should you eat animal-based lard or butter versus a 18:1, it's probably a wash from coronary vascular health. A monounsaturated oil is about as good for you as a saturated. But replace that with polyunsaturated and you see a dramatic improvement in coronary vascular health. Increased trans fats, again, detrimental. Increased omega-6s, beneficial. Now this was really interesting. Increasing omega-3s actually showed to be slightly detrimental for coronary vascular health. Why? When those lipoproteins aggregate at the site of lesions in arterial walls, oxidation has to happen. Omega-3s will undergo oxidation most rapidly. Is it surprising that omega-3s then would have an increased risk for coronary vascular health? Not really. It makes sense. They're more susceptible to oxidation. The one, too, that's really interesting is when you look at neurodegenerative diseases. Again, UFAs, MUFAs and PUFAs, beneficial. Trans, detrimental. Omega-6s, detrimental. So again, if you don't want to die of neurodegenerative diseases, but are okay to die of coronary vascular diseases, you can pick your lipid based on your preferred choice of death. But it's a funny point, but it illustrates something extremely important about saturated fats, and that is that they are essential to be part of our diet. That if you eliminate too much saturated fat, you're going to have detrimental biological outcomes. Saturated fat has to be part of a healthy diet. The problem is in processed foods, we consume too much saturated fat. Yeah?
What's the difference between saturated fat and an animal versus like vegetable?
Huge debate right now. And there's no answer that's really clear. So animal-based fats are predominantly 18:0, right? Now the body has a biological mechanism to convert 18:0 to 18:1. Only saturated fat that can be converted that we know of that can be converted to an unsaturated is stearic acid. Stearic acid is the primary fatty acid found in animal-based fats. Palm-based oils or your coconuts are your medium to long chain. So these are your 14 to 16. These don't get unsaturated by the body. So there's a lot of debate right now on whether stearic acid may be kind of heart neutral, whereas the palm-based oils may be detrimental. Huge debate. Palm oil industry right now is putting all kinds of money into research in this because they don't want that to be. The other thing that, from a reflection perspective of this course, is when you look at Asian diets, palm oil has been a mainstay in their diet for millennia. In North America, palm oil wasn't really introduced until the last 20 or 30 years. So from an evolutionary perspective, people of Asian descent who have been eating palm oil for generations may have a different biological response than people in Western societies who have had introduction of palm oil only very recently. So that we don't really know the effect of chain length on health and outcome, because that's really what you're asking is, do fatty acids of different chain length have different beneficial or detrimental qualities, i.e. does an animal which have longer have more beneficial traits compared to a shorter saturated? There is evidence to suggest that they don't behave the same. The biological outcome or the health consequences are far less clear. So people kind of debate, should you eat butter or margarine? That's part of the question, right? Because margarine is going to have a lot more 16:14:0. Animal is going to have a lot more 18:0 and 20:0. I don't have an answer for you. Literature just doesn't know. We just don't know the answer.
Why does omega-3 oxidize faster than omega-6? Isn't it just something different?
Nope. So remember, the rate of oxidation is dependent on the ease to extract hydrogen. So saturated are about 100-fold slow. So rate of oxidation. Then we have mono. So here we get a hydrogen abstraction. We only get one resonance structure. Then if we have, I have such a hard time with this. Double bond, single bond, double bond. So then here we would have two resonance structures. So this is about 10-fold faster than this. Every double bond we add, we get about a 10-fold increase in the rate in which that hydrogen can be extracted. So oxidizes about 10 times faster, so 18.3 about 10 times faster than 18.2, 18.2 10 times faster than 18.1, 18.1 about 100 times faster than 18.0. The more double bonds you add, the more resonance structures that stabilize it. Now, if we look at dietary fat, what they found was if we take 5% of our diet and replace them with PUFAs, so polyunsaturated fat, all studies indicate beneficial. So if you're going to remove saturated fat from your diet, or if you're going to have a diet restricted in saturated fat, do so by replacing it with polyunsaturated fat. Beneficial. If we replace that saturated fat with carbohydrates, there's no benefit. There's no biological benefit if you're going to replace saturated fats with carbohydrates. Why does this matter? Again, when we talk about the food industry, we have to create palatable foods. If we just pull out 5% of the saturated fat, put 5% polyunsaturated fat, we get a liquid oil. So when you talk about confectionery products, you don't get the same leavening of doughs, you don't get the same lamination of croissants, you don't get the same cookie structure of a crumb of a cookie. So all of this matters from a sensory perspective. Now, it is very easy to replace saturated fats with carbohydrates. So now what the food industry is doing is saying, okay, well, we want to meet consumer demand to reduce the amount of saturated fat, and we're going to do so by replacing it with carbohydrates, because we can create similar structures. We take less fat out, we put more solid carbohydrates in, we get a desirable product. There is no health benefit. So again, when we talk about this scenario, we can't create processed foods that meet this requirement. It's too difficult. We don't have technologies that can structure unsaturated oils into solids. So this, in processed foods, is not a feasible outcome. This can be done, and if we replace monounsaturated fatty acids with saturated, depending on the types of studies they look at, so these are observational cohort studies, these are just looking at your total cholesterol to HDL levels. Total cholesterol, HDL improvement, pooled analysis, no benefit. So again, saturated fat reduction can only be done, or if you want a positive biological outcome, can only be replaced with polyunsaturated fat. Great if you're going to switch to a marine-based diet, eat a lot of cold water fish, you can do it. But from a food processing standpoint, I cannot design foods that do this. It's very, very difficult to do. So not only is it more difficult to structure that food is more susceptible to oxidation. Right? So if I'm going to bake a cookie and I'm going to put a whole bunch of polyunsaturated fats in it, I've got to worry about the temperature I heat it to. I've got to worry if, let's say, in the case of red meat. So there's a lot of studies right now where they want grass-fed cattle, right? They want to have grass-fed cattle because it increases the amount of linoleic acid, the amount of polyunsaturated fats. That's desirable. Well, meat has iron in it. Iron is a pro-oxidant, which accelerates oxidation. Polyunsaturated fats are incredibly susceptible to oxidation. Meat is never eaten raw, it's always eaten cooked. Oxidation is accelerated by heat in the presence of metal, which is in iron, which is in hemoglobin. So is it always the right idea to increase the amount of polyunsaturated fats in foods? And the answer is no. It's not always beneficial. You don't want to use a polyunsaturated oil to go home and fry your French fries tonight. Why? Because the rate of oxidation, the production of radicals, the formation of small aldehydes and ketones are all pro-inflammatory. Those all have implications in cancer. So you have to consider not only the presence or absence of that product from a biological perspective, but also the implications that it has from a chemistry perspective. Is that fat going to be solid? Is it going to have that nice elastic property? Is it going to be stable? Am I going to have to put it in an environment devoid of oxygen? Am I going to be able to cook it? How long will I be able to cook it for? Will it store? Polyunsaturated fats, flaxseed oil, very susceptible to oxidation, will undergo oxidation at room temperature. So just storing your cut of meat with a high level of EPA or DHA in it will undergo oxidation. So all of these things are elements that we have to pay careful attention to when we design foods, especially when we design foods for health-conscious consumers, because we have to make sure that we get the messaging right. So simply saying we have to reduce saturated fats is insufficient. We have to put that precursor in there that when we replace those saturated fats, it cannot be with carbohydrates, it cannot be with monounsaturated fats, it can only be with polyunsaturated fats, and there's limitations to when we can put those polyunsaturated fats into foods. And we have to look at it holistically. So we have to look at it from a manufacturing perspective, from a consumer perspective, and from a patient outcome perspective. So it's really, really complicated when we start to say, okay, the nutritionist wants you to eat this. So now I have to go and I have to reformulate that food, and that food may not be able to be reformulated with that in it. So we need a complete paradigm shift to how we structure our diet. And that's kind of where we are in society today. We have seen that longevity is being determined by diet-related chronic diseases. So if you're happy living to 76, 78 degrees, eat the Western diet. We know we've got you that far. If you want to live to be 80, 90, 100, we need to completely rethink how we process foods. Now some of you are sitting there, I'd never want to live to 80, 90. Wait until you're 40. Time goes by so quickly. So with that, we're done lipids. We'll have one lecture on proteins, and then we'll move into next week.